Right, we'll get going again. So the second part of the lecture today is going to be talking about nuclear power. And nuclear is very political. It strongly divides opinion. What I'm going to try and do in this lecture is really go through the science facts of what energy can be generated, how much energy, and it is extremely low CO2 per kilowatt hour compared to even renewables and many renewables. So in fact, if we look in the UK, nearly 8% of total energy and 20% of all electricity in 2017 was nuclear. And those numbers are going to change in the future, as I'll explain, mainly because the UK hasn't, the politicians have not made decisions early enough to now allow new nuclear power stations to be built. What that will mean is that the UK's electricity is going to have a lot more CO2 emissions in the future simply because new nuclear has not been built. Because the only way to fill the gap in the timescales required is going to have to be using gas-fired power stations. Now, nuclear in operation emits very little CO2, but it's the building, fuel processing, transport, and decommissioning that we end up with these figures of between 14 and 20 grams of CO2 per kilowatt hour in terms of the latest pressurized water reactors. And I'll show in detail later some of these reactor designs. Now, in effect, what you have, this is Hunterston B advanced gas reactor that's about 28 miles from Glasgow. And it's a Rankine cycle power station, but it's using nuclear fission to actually heat the water. So the first thing we're going to do today is look at how nuclear fission actually creates heat and how that's used to run a Rankine cycle power station. So I know many of you will understand about atoms, but we'll just go through it in detail. Of course, we have a nucleus that is made up of protons and neutrons, and we have electrons around the outside. The key thing in this lecture is knowing how to write each of the elements. So here's carbon. It has 6 as its atomic number, so it has 6 protons, but it's actually got 12 protons and neutrons. And so what we have here is 12 nucleons and 6 protons for carbon. So the mass of the atom ends up being less than its constituent protons, neutrons, and electrons by some change in mass delta M. And this is what Einstein, of course, was very famous in showing, that in fact the binding energy in an atom is this change in mass times the speed of light, c squared. So this ends up being a very large number because the speed of light here is 3 times 10 to the 8 meters per second squared. And in fact, you can look up different tables. You can get this nucleon binding energy, and there's a maximum that you get somewhere around iron with 56 nucleons in the periodic table. Now, what this really means is that, as you'll see a little bit later, when you're lower than the value, the nucleon binding energy for iron, you can actually get more energy out of a system by fusing atoms together. And we'll talk about that at the very end of the nuclear section. This is how the sun operates. It's still very much a research project, and it's not something that works efficiently yet. Then we also have how all the nuclear power stations generate electricity at present, and that's using fission. And that's basically where we take a large atom and we split it into smaller atoms. And that process of splitting releases a lot of energy, and the energy produces heat, which heats up water in a Rankine cycle steam engine. So nuclear fission is the process where we take some fissile element. Now, typically it's uranium-235 or plutonium-242 are the elements that are actually used in nuclear fission power stations. To make uranium a fission process, we actually have to add a neutron. I'll explain how we do that in a few slides' time. That generates uranium-236, and uranium-236 is unstable. So it spontaneously splits, forming two fission products. Here, what I've shown is barium and also krypton, and then a whole series of radiation that comes out of alpha, beta, gamma, and as well as other neutrons that get emitted. So you can see, in fact, the neutron that comes in, we end up with neutrons coming out. And if we run this correctly, the neutrons coming out can actually start more fission processes, and we can create a self-sustaining reaction. Now, I've shown barium and krypton here. Actually, there are many different fission products that come out. And quantum mechanics, when you calculate this, there's a random, well, there's a probability of different fission products appearing. So it's not just barium and krypton. But what we do have to have is that the number of protons on each side has to agree, which is the bottom here. So 92 has to equal 56 plus 36. And if we look at 235, well, we have plus one neutron, so it's really 236 has to equal the 141 plus the 92 plus the 3 neutrons. So this is just, you just need to balance both sides of this equation, that you've got the same number of nucleons on the top and the same number of protons on the bottom, on the left-hand side and the right-hand side of the equation. Now, we've got neutrons coming out that we show in this equation. There's other radiation types as well. So alpha radiation is where you have a helium nucleus, and that's typically where you have 2 protons and 2 neutrons. Beta radiation is electrons coming out, and gamma radiation is high energy photons of light. So this basically is higher energy photons than you have with X-rays in the system. And you can also have neutrons coming out, and all these are different radiation forms that come out of nuclear reactors. Now, when we look at alpha radiation, in fact, a sheet of paper is sufficient to block alpha radiation. So while this is the most dangerous to humans, actually it's very easy to shield against, even with simple pieces of paper. Beta radiation and gamma radiation, and for that matter, neutrons as well, require either very thick, dense metals or reinforced concrete plus dense metals to actually shield from them. And this is why nuclear reactors really required significant shielding around them to protect the humans that are close by running the reactors. Now, there are, as I've said above, there are many different forms of reaction fission products that are possible. But all these radiation forms that come out, as well as the kinetic energy of the different fission products and the neutrons, create heating through absorption, so through scattering in the gas, that we have these processes going on, or the solids and the gases. Now, not every neutron coming in will actually create a fission reaction. And in fact, it's only neutrons with relatively low energies compared with all the neutrons you have coming out in the fission process that actually start a new fission process. So what you need to do with fast neutrons, they cannot be captured by the uranium-235. And so you have to reduce the energy. Now there's different ways of doing that, but typically what you do is you add some light atom, what are known as moderators, and you slow down the fast neutrons to much slower energies where they can be captured by the nuclei to undertake new fission processes. So these light atoms are called moderators, since they moderate the neutron speed to lower speeds. And graphite and heavy water, so where you've got deuterium oxide, are good moderators. So these are the 2 moderators you'll see in different reactor designs when we go through those a little bit later. So how much energy can we get from fission, or for that matter, from fusion? Well, what I'm going to show you in this slide and the next slide is really the way you can look at different fission or fusion processes and calculate how much energy you can get, not just from one fission process, but from a kilogram of fuel. So first we need to define, we're going to call A1 the mass number of atom 1. We're also going to have atom 2 and atom 3. So A2 will be the mass number of atom 2, and so on. We need to know the binding energy. So this is what I gave the graph a few slides back. It's the binding energy, and we can look up each of the atoms. So we need to know of atom 1, of atom 2, and the other atoms in the fission process. So we're going to have in our fission process, what we showed before was uranium, and it was actually 236, forming barium, krypton, and some sort of energy as well comes out of the reaction. So we want to calculate this energy that is released in the nuclear fission reaction. Now, to do that, what we end up having is the mass number of atom 2, so that's one of the fission products, times, in brackets here, the binding energy of this fission product, minus the binding energy of the original atom before fission. So you can see what we do here is we take the mass number of one of these fission products, and then we have the difference between the original binding energy and the binding energy of the fission product that's formed. And what we have to do is do this again with however many fission product atoms actually come out. So it could be 2. In some fission reactions, it might be 3. Typically, it's 2 for the majority of uranium and plutonium that's actually used in nuclear reactors. So the next part we need to do is look at the fission product atom 3. And we have the mass number of atom 3 times the binding energy of atom 3 minus the binding energy of the original atom before fission took place. So we just repeat this again if we've got more fission products coming out. Now, it's much easier to explain this by giving an example, and we're going to do the example of what you saw in the fission example above. So we had a neutron plus uranium-235, and it went to barium-141 and krypton-92 plus 3 neutrons. Now, if we look up in binding energy tables or in the graph that I showed you, then the binding energy of uranium-235 is 7.6 million electron volts. So an electron volt is 1.6 times 10 to the minus 19 joules. So this is typically used in either electron volts or mega electron volts because it's much more appropriate for the amount of energy that you get in binding energies. If we look at barium-141, it's 8.3 mega electron volts, and krypton-92 is 8.5 mega electron volts. So you can see here that you have more energy, binding energy for the smaller atoms compared to the larger atom of uranium. And so when we end up with the two split and doing these equations, you'll see we always end up getting a positive and larger binding energy, energy released out. So we just go through the numbers. Well, for barium, the mass number is just 141. So it's just the number of nucleons you have in the atom. So we have 141 at the start. We then have, if we look at this, the binding energy of barium, and that's 8.3 mega electron volts. So here it's 8.3 times a million if we're going to do it in electron volts. And then minus the binding energy of uranium-235, that's 7.6 mega electron volts. So it's minus 7.6 million electron volts. We then have to do the same for krypton. So we've got 92 as the mass number of krypton, just the number of nucleons, times the binding energy of krypton. Well, that's 8.5 mega electron volts, so 8.5 million electron volts, and then minus the binding energy of uranium, so 7.6 million electron volts minus 7.6 10 to the 6. So this equation is all in electron volts. So if you go through this calculation, we'll end up with 182 million electron volts or mega electron volts. And if we multiply that by 1 eV to get the number of joules, that's 2.9 times 10 to the minus 11 joules. So, this is just for one example. Now, in fact, on average, if you use a nuclear reactor with uranium-235 as the fuel, the average in terms of the fission products gives you about 157 mega electron volts. So this is just one example. It's a little bit bigger than the average, but you can see how you calculate it for all the different potential fission products that you might get in a nuclear fission process.
Excuse me, Professor.
Yes.
Yeah, according to the equation, it's A2 in A2 bracket start EB into A2. So EB, in this case is 8.3 into 10 raised to power 6. We have to multiply it with A2 also, na? That is the atomic number of the beryllium. That is 141. And then for the uranium, we have to again multiply with the atomic number. Sorry, the mass number of the atom.
It's just the mass number. It's not the atomic number.
Sorry, mass number.
And as you can see here in calculating it, we're not actually interested in the uranium mass number.
But according to the equation, it's EB into A2.
No, this is just, sorry. What this is, it's the binding energy of atom A2.
Okay.
So this is what apologies if this wasn't clear, but it's what I've written. This is just atom 2, and in this case, atom 2 is 141 barium, and it's 8.3 mega electron volts. Okay. Sorry about that if it wasn't clear. So let's say we take the average fission value for uranium 235. So we've got 157 mega electron volts, 2.51 10 to the minus 11 joules released per uranium-235 fission. How much energy do we get out per kilogram? So this is what we want to do, because a kilogram is a much more appropriate amount of uranium-235 fuel than one atom. Now we need to actually look at how much uranium-235 is actually used in fuel. Now natural uranium only has 0.7% uranium-235, and it's 99.3% uranium-238. Now there's also traces of other different isotopes, such as uranium-234, but natural uranium is dominated by uranium-238. Now, uranium-238 doesn't give you fission directly. You can do other things with uranium-238 to modify it into another atom that ends up giving you fission products. But directly, uranium-238 doesn't produce fission. So what normally happens is, in fact, you want to increase the percentage of uranium-235. So the nuclear fuel is enriched with additional uranium-235. So in fact, most nuclear fuel has about 3% uranium-235. And basically synchrotrons are used to separate out the different isotopes with different masses. And then the uranium-238 is naturally enriched to have a higher percentage of uranium-235. Now, I should also say that this number is way below the concentration of uranium-235 used in nuclear weapons. I'm not going to go into weapons at all here, but this is well below what's actually used in nuclear weapons. That's deliberate, so this couldn't actually be used to make weapons. But if you take enough fuel out of nuclear reactors and you have synchrotrons and you take out all the uranium-235, you could potentially make a weapon. And this is why there's a lot of security around nuclear fuels. And this is part of the issue of different societies using nuclear. There's a security threat that somebody could always steal that fuel. and if they had sufficient resource and expertise and capability, potentially make a nuclear weapon out of it. Now we need to work out how many atoms we have in a kilogram of uranium. So 1 mole of uranium is 238 grams, so 0.238 kilograms. And Avogadro's number is 6.02 times 10 to the 23. Avogadro's number is the number of atoms in 1 mole of a material. So 0.238 kilograms of uranium has 6.02 times 10 to the 23 atoms. So the number of nuclei per kilogram is Avogadro's number divided by the mass of 1 mole. So that is 6.02 times 10 to the 23 divided by 0.238. Now what I should say is that particularly with American textbooks, you will see moles in grams, so it will be 238, and you may see Avogadro's number in terms of grams as well. So you might see some things that are a little bit different depending on which textbooks you look at. But the number of nuclei per kilogram is 6.02 10 to the 23 divided by 0.238. And if you do that sum, you can see that 1 kilogram of uranium has 2.53 times 10 to the 24 atoms. So we calculated the fission for 1 uranium-235 atom. The energy released per kilogram, well, remember our fuel only has 3% uranium-235. So it's been enriched to get 3% uranium-235. So we need to multiply by 3% times the number of atoms per kilogram. So 2.53 times 10 to the 24 times the energy released. So this is 157 mega electron volts. So 157 times a million for the mega, and then times the electron volt times 1.6 times 10 to the minus 19. And if we calculate this number, then you end up with 1.9 times 10 to the 12 joules. So this is 1,900 gigajoules of energy. So to give you an idea, this is nearly 1 million times more energy than fossil fuels for 1 kilogram the amount of energy you get per kilogram is 1 million times higher than you would get from any fossil fuel. So compared to coal, 1 kilogram you have here provides 1 million times more energy than 1 kilogram of coal. So you can now understand why there's so much interest in nuclear fission. For 1 kilogram of fuel, you get 1 million times larger the electricity than you get with fossil fuels. Now, there are other things in here that it's not quite exactly 1 million, but typically it's a few 100,000 is what you end up with real practical systems. Now we spoke about a single fission process. So a neutron coming in and the 2 fission processes come out, perhaps an alpha particle and neutrons. We get multiple neutrons in certainly uranium-235. Some of those neutrons will hit a moderator atom. This is carbon, so using graphite. It slows it down, moderates it. That neutron can then undertake another fission reaction. And then the same can happen again. So we end up with the dotted product, some neutrons. The neutron hits a moderator. It goes into another uranium-235. It goes through a fission process, and we end up with more neutrons coming out. So when one neutron creates this whole process, it's called a chain reaction. As you can see, it's a bit like a chain being linked if you look at the neutrons going through to create the next fusion process. So that's what you want to generate electricity, that you don't have to put too many neutrons coming in. You only need 1 or 2 to start the process, and then it's a self-sustaining chain reaction. Of course, what you don't want to happen is where all 3 or 2 of the neutrons coming out create fission processes. This grows exponentially. And this is what you do for a nuclear weapon to make a bomb, and you get an explosion. So you can see you want a self-sustaining process, but you don't want so many neutrons forming the next fission processes that the whole thing grows too fast and you can't control it. Now, in fact, the way all nuclear power stations are run is to be a little bit below that one-to-one chain reaction, because there's always extra neutrons coming naturally from the spontaneous decay of some of these large atoms in the fuel. So let's just have a quick look at the reactor designs. So if we look first at, this is a British design reactor. It's the Advanced Gas-Cooled Reactor. It's not the first nuclear power stations. They were Magnox. So the first nuclear power station in the world was at Chapel Hall in the UK, and that was a gas-cooled Magnox reactor. But in the UK, they actually use CO2 as the coolant for the reactor core, and the CO2 also transfers the heat from the reactor core into a heat exchanger with the water. So this is all set up so you have the highly radioactive side, and then the water going through the Rankine cycle power station ends up not being radioactive and being relatively safe. So here you can see those control rods. The control rods are actually materials that absorb neutrons. So if you push the control rods the whole way down, then what they do is they absorb neutrons and they stop the fission chain reaction and reduce the heat coming out of the nuclear reactor. When they're pulled up, more and more neutrons can go between the fuel rods, and you get a larger chain reaction and you get more heat coming out. These designs are all built with safety critical systems in mind. So the control rods, if there's some mistake or the power goes off, they drop in and they shut down the reactions and they shut off the reactor. If you look at Chernobyl, one of the problems with the Chernobyl and the Russian design was that the control rods went in from the bottom. And so when they got a problem, they couldn't actually push them back up to shut down the reactions. Now, the most common nuclear power station that's been built around the planet is the pressurized water reactor. And the idea here is that you're using water to actually go around the fuel and take the heat away. Now, this actually is more efficient at taking the heat away from the fuel when it's generated, but it has a big disadvantage. The temperature that can go on here, that you can actually end up splitting the water into hydrogen and oxygen if you do not keep it under a high pressurized circuit. So if this breaks, then you can end up having the high pressure, high temperature water being split and forming hydrogen and oxygen combine in an explosion to create water. So if you look at Fukushima, where they ended up having an explosion, that was because it was a pressurized water reactor. And there ended up being a break in this pressurized water loop to take the heat away from the fuel. And it was the hydrogen and oxygen recombining and exploding that blew the top off this containment vessel that keeps the radiation and is there in case there is an accident like that. You then also have another heat exchanger to basically transfer heat into the water that goes around the Rankine cycle generator. So as I said, this is the majority of the nuclear power stations designed, and the modern versions of these, the generation 4, really end up with very low amounts of fuel and being very efficient in terms. To give you an idea, a Gen 4 power station, well, I'll do the calculation later, but you end up with something like, I think it's 8 cubic meters of waste after something like 40 years of running the power station. Now, this is the Canadian deuterium uranium reactor. It's known as the CANDU reactor. There's still a few of these running in Canada, but there's not so many of them around anymore. And here what they're doing is they're using, rather than water, they're using heavy water, deteriorated water, and that acts as the moderator, but it also acts as the coolant and takes the heat away from the reactor core before there's another heat exchanger to transfer to the water going around the Rankine cycle to generate the electricity. So Canada really developed this system. It's the only country that really went after heavy water-based systems, and very few of them now remain. So here's a couple of questions I'll answer in a few slides. What is the volume of waste for 1 gigawatt per year from a nuclear power station? So has anybody got an idea what volume of waste we might get for 1 gigawatt?
Couple of hundreds kilogram.
100 kilograms, thank you. I was really after a volume, but 100 kilograms, we can probably work out with the density what that's going to be. Okay, I asked this question, but again, it's very seldom people know the answers. Now here's an interesting one, because it's very seldom I see this comparison between nuclear and coal. But what is the volume of waste, or the CO2 volume you get from 1 gigawatt generation from a coal-fired power station? So does anybody know the number for this, or can guess what the volume might be of carbon dioxide coming out of a gigawatt power station in 1 year? Guess.
Maybe 0.
0? No. So a coal-fired power station, this is the carbon dioxide emissions out of a coal-fired power station.
1 million tons.
Okay, thank you. Well, you got that it's 3,200 tons per hour, but that wasn't for a gigawatt year. But it at least gives you an idea it's going to be a large number. Well, before we get there, we'll have a little bit of a look at the nuclear cycles. So before we actually get to the reactor where we generate the electricity, we end up actually having to mine and extract uranium. Now, you hear a lot in the media, people saying that building this nuclear reactor and with all the concrete, it's going to be an enormous amount of CO2. Well, we'll go through this in detail in the last lecture, but actually because these things generate so much electricity, it ends up being a very small percentage of the CO2 being the concrete and the building of the power stations. Almost all the CO2 emission from this process is the mining and the enrichment and fuel fabrication. So most of the carbon that's generated in this whole process comes from the energy required to do these particular processes. We'll go through that in the next slide in a bit more detail. You end up with this, throwing away loads of depleted uranium and things you don't need. And also from the mining, there's a lot of waste that gets thrown back. Now, once you have the fuel, that goes into your nuclear reactor. Once the fuel has been spent and used and you've generated electricity, it basically gets stored on site for what's known as short-term storage. That typically can be a couple of years. But as it comes out of the nuclear reactor, it's highly radioactive. Now, there are a lot of long-term nuclear elements that you have to worry about, but actually there's a lot of fast decaying fission products that if you leave it in water storage short-term on site, you can decay the radioactivity quite significantly. And it's still not completely safe, but it's safer to transport and give long-term storage, or as you'll see, a lot of this actually gets reprocessed and recycled and actually used back in enrichment and fuel fabrication. So how much nuclear waste from 1 gigawatt per year? Well, the first thing we want to work out is how much fuel we need for 1 gigawatt of electricity. So this is the cycle from mining all the way down to getting 1 gigawatt per year of electricity. And we'll run backwards so you can see how much material you have to mine to be able to get 1 gigawatt of electricity out of a nuclear power plant. Now, if you go through the efficiencies, so a typical Rankine efficiency is 34.2%. You can work up the burn rate of the fuel to generate electricity. We're not going to go through in detail how you do that in the course, but you can do that. And you work out that you're going to get 28.8 tons of spent fuel coming out at the end of each year. So that's what remains after you've actually generated your 1 gigawatt year of electricity. To be able to get that of spent fuel, or waste if you like, you need 28.8 tons of enriched uranium. Now for the UK reactors, they actually use uranium dioxide. That's because uranium dioxide melts at a much higher temperature than uranium. So it helps, it's a safety issue. Uranium dioxide is a much safer fuel because the melting point is significantly higher than uranium. So you need 28.8 tons of enriched uranium oxide. Now to get that, you actually do an enrichment process that generates uranium fluoride. You need 38 tons of enriched uranium fluoride to get the 28 tons of your fuel. To get to that 38 tons of uranium fluoride, you need 305 tons of UF6. So this gets enriched to take the uranium up to uranium-238. In fact, in this case, it's 3.6% uranium-235 enriches the uranium-238, and you still throw away a lot of uranium-238 in this process. To get the uranium fluoride, you need uranium-3 oxide, or U3O8. So this is a uranium oxide, which you get out of the ore. So you need 245 tons of this. To get the 245 tons of uranium mill, you need over 108,000 tons of ore. So in terms of mining, you're ending up having 542,000 tons of waste rock as waste from the mining process to get your 1 gigawatt of year of electricity. Now, I know this is a little bit complicated. It's worthwhile after the lecture reading through in both directions to understand, but you need to mine a lot to get very little that you need to generate the 1 gigawatt of electricity down the end. So 1 gigawatt per year. Let's work out what volume of waste this 28.8 tons ends up being. So most carbon emissions, as I said, comes from this whole process. So 28.8 tons of spent fuel. Well, uranium density is 19,050 kilograms per meter cubed, and the barium density, which is one of the daughter products, is 3,590 kilograms. That barium is the lightest fission product. So somewhere between these two numbers is the volume of waste we get out of a nuclear power station for the gigawatt year. If we divide by uranium, we end up with 1.5 cubic meters. Or if we divide by barium, we get 8 cubic meters. So in reality, a nuclear power station each year is actually producing about 4 to 5 cubic meters of nuclear waste. 4 to 5 cubic meters. Now let's compare that to a coal-fired power station and the carbon dioxide that's emitted. So coal has 0.96 kilograms of CO2 per kilowatt hour on average. Now I know some coals are, ignite coals in particular, are worse than that. The density of CO2 is 1.98 kilograms per meter cubed. if we look at a gigawatt year for a coal-fired power station with a typical efficiency, it will produce 8.4 billion kilograms of CO2 for each gigawatt it produces per year. So, this is 8.4 million tons compared to uranium's 28.8 tons. And if we use the density to work out the volume, we're talking about 4.2 billion meter cubed is the volume of CO2 released for every gigawatt year out of a coal-fired power station. So the waste that a coal-fired power station produces with CO2 is this enormous volume compared to a volume of 4 to 5 cubic meters for a nuclear power station. So you can now see, people complain about nuclear waste. Yes, it's radioactive, but the volume of radioactive waste compared to the volume of waste out of a coal-fired power station is tiny. And this is the energy density coming in and really making a big difference again. Now, we still have to store what's left over from this. So one of the big complaints about nuclear fuel is that some of the waste that will have to be buried into long-term storage. And this is long-term storage that potentially will be thousands, if not hundreds of thousands or millions of years for some of the fissile waste that ends up being remaining and radioactive waste. So the argument against nuclear is that we're using the energy now and we're burying the waste for future generations to have to deal with and worry about if this will leak out or remain stored. So it's a similar argument to the carbon capture. It won't be our generations that have to deal with this, but potentially future generations have to worry about the waste that we have stored. But actually, what I showed you was just the straight, let's not recycle some of that waste. In reality, what happens in nuclear is that once you've run once you've got the waste coming out after generating electricity, you've got spent fuel, but you can actually recover a number of different elements out of that spent fuel. So what happens in the process with uranium-238, whilst uranium-238 doesn't actually go through a fission process, it can go through processes where it can form, after a couple of reactions, plutonium-242. It can also form uranium-235 by basically getting rid of, actually having a proton being absorbed and then an alpha particle is emitted. You end up with a uranium-235 atom, which is fissile, remaining in the nuclear waste. So the point about this is the nuclear waste that comes out of this power station will actually have new nuclear fuel that can be recovered, what's known as mixed oxide fuel that can be recovered, and that can be put back in and used again as new fuel. So this is the natural uranium that you get from the mining process. That goes into your conversion enrichment plant, and you get unmixed oxide fuel. You then have this process that you take the spent fuel, you separate out the plutonium, and you basically get plutonium and uranium-235 that can be put back in to enrich the fuel that's being used. And this actually further reduces the amount of spent fuel and waste that come out of the process. So the numbers I gave you in the previous slides, in fact, they're less than those numbers because a lot of the heavy elements and new fuel that's generated can be recovered. And this is known as Purex. It's plutonium, uranium recovered by extraction. So nuclear issues and politics. Well, high initial capital costs and decommissioning costs. So we'll talk about this in great detail in the last lecture when we look at the economics of different forms of power station and fuels. But the real problem with nuclear is an extremely high capital cost. So some of the new nuclear power stations are talking about 20 billion euros as the cost to build it. And that limits who can do it. The other thing is that the decommissioning, well, the building, the running and the decommissioning can end up being 140 to 150 years of lifetime. And that's very difficult for private companies to invest because very few humans will actually survive the length of the plants running. There are accidents, and the accidents release nuclear materials. And those nuclear materials and radiation are dangerous and hazardous to humans. So what I should say is all the accidents to date have been due to humans. None of the accidents in nuclear power stations have been related to natural disasters. So even Fukushima and the disaster at Fukushima in 2011, whilst it got hit by a tsunami and an earthquake of 8.5 on the Richter scale, it survived that. And the reason there was an accident and it released a lot of radiation was because the people operating the plant tried to actually keep it generating or keep it in a state it could generate electricity in the future, rather than when there was breaches to parts of the water core to actually be able to so what happened was there was a breach, and rather than humans shutting it down, they tried to keep it in a form of the reactor to be live rather than shutting it down completely and forever. Now, if you look at all the other accidents, Windscale was the first one in 1957. It's been shown about 240 additional cancer cases with the effect of the radiation that came out of that. In the US, the 3 Mile Island accident in 1979 released radiation into the atmosphere. It's been shown that there's no additional effects on human health from that radiation release because it was very low. Chernobyl in 1986 is probably the biggest nuclear accident in history. There were 28 deaths almost immediately afterwards, and a further 14 from the 128 high-dose individuals who died within 10 years and had gone in to try and fight the fires and shut down the reactor. But actually overall, the number of cancer cases and so on, even from what was quite a serious and major nuclear disaster, is still very low compared with, for instance, a pandemic or even the deaths you get from bronchitis and radioactivity out of coal-fired power stations. The most recent Fukushima was 1 death. There's been a few hundred cancer cases expected due to the radiation leaks, and that we'll have to see what the numbers be. So you've got to put this into perspective. I know accidents happen. With nuclear, they can kill people. Society tends to be much more worried about these than actually the number of fatalities and the illnesses that come from them. With radiation, well, coal-fired power stations, all coal has radon gas, about 1%. That goes into the atmosphere. And even compared with the worst Chernobyl or Fukushima accidents, the amount of radon and the radioactivity from that going into the atmosphere per year from a coal-fired power station is greater than the total radioactivity from any of the nuclear disasters. I had to look that up and check it. I struggle to believe that, but it's true. But the big sticking point is really waste, storing and disposing of nuclear waste. Security. You cannot make an atomic bomb from nuclear waste or from nuclear fuel, but you could make a dirty bomb where you spread radioactivity using conventional explosives. So this is a much bigger worry. Also, the fuel could be taken, and with the right resource, you could potentially get out material to make bombs, which is why security is such a big issue. Now, nuclear fission is not long-term sustainable. And that's because the fuel is limited. Now, certainly compared with fossil fuels, it's much longer So at present, there's sufficient uranium in mines and the known mines for 500 years to power the present nuclear power stations. Of course, if more nuclear power stations are built, that figure will come down, but that's just looking at uranium and from mining. You can also extract uranium fuel from the sea, from water. The oceans have a small finite quantity, but as you've seen, you don't need very much uranium to actually be able to power nuclear reactors, and that could actually provide 8 times more. So for the present number of nuclear power stations, you can see this is getting into over 3,000 years worth of powering them. There's also in water a lot of plutonium and thorium, and in fact, thorium, there's a Swedish project looking at a thorium cycle nuclear reactor. The interesting thing with thorium is while it's less dense and it releases less energy, you cannot build a weapon using the thorium cycle. So it's a much safer form of nuclear cycle that can be not used for weapons. Right, we're coming to the end of nuclear, and I want to finish off by talking about fusion. So fusion is the process that happens in the sun, and it creates all the light that we use for solar through heating or for photovoltaics. And fusion is the process where we take 2 different atoms and they're fused together to create a bigger atom, releasing typically neutrons and a large amount of energy. Now you can see here if we take hydrogen 2 and hydrogen 3, so deuterium and triton, you end up with helium, a neutron, and what is about 10 times lower than we got in the fission process per atom. The point about it with density and the number of nucleons is if we divide by the number of nucleons, this is a lot more energy per nucleon than you get from a fission process. So actually fusion gives you a lot more energy per kilogram of fuel. The deuterium here comes from water. Now, in fact, it was a Russian that showed tritium is actually a difficult one to produce, but there is a process with a neutron and lithium, and there's millions of years supply of lithium on the planet. So you can use this process to get the tritium, and you can use water to get the deuterium, and this ends up being how you get substantial energy from fusion. Now, there's been a lot of research projects. In Europe, we've had what's known as the Joint European Torus. It's being run in Oxfordshire in the UK at the moment. At the moment, they've only run it for a few milliseconds to generate a self-sustaining fusion reaction. Milliseconds. And they have created more energy out than they've put energy in. The problem with fusion is that fusion happens at 10 to the 8 Kelvin temperatures. So this is an enormous temperature, and so you have to electromagnetically confine the plasma that this nuclear fusion happens in because the temperatures are enormous. So to be able to confine where the fusion's happening, you've got to keep that well away from any materials. You are getting radiation and neutrons and alpha particles coming out, but in fact, a lot of these can easily be held and confined in here. Potentially, it's limitless in terms of energy, as the density is enormous, even compared to fission. And helium is the waste product, which we know has relatively low greenhouse gas issues, and there is no or very little CO2. There probably will be CO2 in some of the mining and production of lithium and maintaining the power station, but it's extremely low compared with all the numbers that we're actually talking about. But as I've said, this is very much a research project. You can look up the facility at Culham in the UK and see the latest results in that at the website that's there. But the joke about nuclear fusion is it's 50 years away, and it's always been 50 years away. So there's not been very much progress in making a practical fusion reactor that you can get electricity out of. And that's where we basically are with fusion. Now, in fact, if you want to solve greenhouse gas emissions and solve a lot of the energy crisis at the moment, one argument is that you really want to have an enormous global effort to produce nuclear fusion electricity generation. And that would be one way that you could solve a lot of the climate change problems. But that's one argument. There's many arguments against that as well. And that's probably where I'd like to leave the nuclear. And this is a good time for question and breaks. So I'll stop the recording. Oops. So has anybody got any questions? So there's one in the chat about what is radon gas. So radon is just an atom in the periodic table. And it's just a gas that naturally decays to form, I think it's beta radioactivity. So you end up getting electrons being emitted from the nucleus naturally. Radon gas is actually found in many different parts of the world. It's also in a lot of granite rocks. So you tend to find that granite rocks provide larger levels of background radioactivity. So the other question in the chat, suppose after reaction some excess neutrons remain, what happens to the excess neutrons? Well, you need here you actually use the excess neutrons to power the next part of the process, to create the fuel. And so this actually is a self-sustaining process. What you have with the fission reactions that we were showing earlier is that, yes, there will be some additional neutrons. These basically are radioactivity and will get absorbed either by the control rods or get absorbed by the reactor shield. And so that's typically what goes on. Some of them will be absorbed by uranium-238, which dominates the uranium-238 fuel. That creates uranium-239 that then decays to form uranium-235 that can go through a fission reaction. So there's multiple things that can happen to the excess neutrons, but either they're absorbed, well, they were absorbed either by the reactor core or by uranium-238, and then that forms more fuel for the future. Well, the self-sustaining really depends. It can go on until the fuel burns out. Normally for many of the nuclear power stations, they're typically fueled for many years. So, it's self-sustaining can actually go on for many years. Any other questions? If not, what we'll do is we'll have another short break and we'll start the final part of the lecture at 4 o'clock.